Hi folks, welcome from Cambridge in the UK. I'm Mikhail Jacob, and I'm a postdoctoral researcher with Microsoft Research. This is my talk on human-AI co-creation for games and game creators. My talk today will cover some of the interesting possibilities when we use artificial intelligence as a part of our creative processes or creative practice. This is also known as human-AI co-creation. I'm going to talk about my original research in this space, but really, the use of AI techniques is already a part of our creative processes today. We already use AI tools to explore new ideas and get inspiration. This is an example from PowerPoint design ideas on a slide for our development sprint review, which the system took quite literally. We also use it to automate away some of the tedium in our creative work. This is content-aware fill in Photoshop. There are even examples where systems can collaborate with us to create original creative outputs that would not have been possible without each collaborator, human or agent. This is an example called Drawing Apprentice, where you can take turns to create abstract sketch art with an agent. But how do we apply co-creation to games and game creators? I'll be talking about that today in two parts. First, I'll talk about how we can apply this co-creative process to generating emergent gameplay with game characters. Then I'll talk more about how we can apply some human-AI co-creation to the actual process of making games itself. Fantastic! Let's dive into co-creating gameplay with agents and see how far we can take this concept. Well, as an extreme example, why not just let the characters in the game make everything up as they go? Let them really co-create the gameplay with you while you play it. I'm talking, of course, about improvisation. These are all real-world creative practices where people co-create a story, or a play, or a scene, or just expressive improvised interactions together in real time, without clearly specified goals or too many hard constraints on how they behave. So why don't we have games where all the agents can make things up as they go, roll with your creative punches, and serve up their own creative offers to make things interesting? Because, as it turns out, it's really hard. This applies to human improvisation too, in many cases. There are many challenges that improvisers face, real or virtual. Let me tell you about two key problems that I think are particularly important for AI improvisers. I'll do that by showing you two game experiences we built, where we tackle these specific problems and enable you to improvise with your AI. This work was done with my previous colleagues in the Expressive Machinery Lab at Georgia Tech. For our first problem, let's talk about improvisation in partner dancing. Partner dance is ubiquitous around the world. It's usually improvisational. There's a focus on acting and reacting to your partner. We were interested in creating improvisational partner dancing games where the agent didn't just use a fixed set of moves or expect you to learn its moves before you could really dance together. But the primary problem faced was the knowledge authoring bottleneck. This is the problem of needing a vast amount of knowledge authored by a system designer before the agent can do anything interesting at all. In this example on screen, the robot knows exactly 3 things to respond with, so it can keep doing them again and again. As in life, that makes it a really boring dancer. Our solution was to learn from our users. Learn to dance with future users by observing current users. Learn not just dance moves, but how to sequence these dance moves together sensibly. We used a few different tricks to make this work. First, when we learned gestures from people, we clustered them together so we could reason about how to use them at a higher level of abstraction. Then, in order to understand how to sequence these gesture clusters together, the agent learned patterns for using them by watching how humans responded to its moves. By observing how people reacted to the agent's actions, it could tell how to react to future partners if they did a move similar to what it just did. And since learning these patterns of interaction required a lot of interaction, in many cases the agent didn't recognize what the user was doing. For these novel situations, the agent used procedural strategies for generating responses, like mimicry or imitation, or transforming some element of their action and using it back with them, or recalling similar but different dance moves from the past and using them instead. Here's a demo of what that looked like in action in the Lumini installation. Note how the agent starts moving beyond mimicry and imitation when they start dancing in rhythm. Great. The main thing you can take away from this work is that the knowledge authoring bottleneck for improvisation can be avoided by carefully learning as much as you can from your users as quickly as possible. You can find more detail about the Lumini installation, as well as other problems we tackled on the way to creating an installation like this, in the papers and videos at the link above. Lumini was a novel game experience and was successful at improvising dance with an agent. But it is still quite far from agents that can improvise anything like the structure and narrative needed for many games. So, taking some further baby steps in that direction, we decided to look at simplified improv theater. Specifically, we were interested in creating a heavily constrained version of the short-form improv game called Props. The Props game has actors receive a prop, usually an abstract prop of some kind, and pretend that it is a real or fictional object. Then they use that pretend object in a scene or a story, or just a comedic one-line interaction between partners. That's the version we targeted. Importantly, the game is widely open-ended, and your choice of actions is not restricted by clear goals or hard constraints. The only real constraint is the prop and what it reminds you of. This is relevant to studying the other key challenge for improvisation with AI, the improvisational action selection problem. That is, how can an agent choose actions in near real time from an extraordinarily large number of options without clearly defined goals or constraints? Inspired by the various arcs that can be perceived in other art forms, we proposed a general method for motivating action selection in these open-ended improvisational settings called creative arc negotiation. A system designer provides the agent with a target creative arc to follow. This is not a list of actions to follow, but a set of target values for the novelty, unexpectedness, and quality estimates of the agent's actions during improvisation. Then, while improvising, as long as the agent is following these target values along the arc, balanced of course by estimates of the human's actions, it can do the first action that comes up with. Let's take an example. Given a rising creative arc, the agent would be tasked at first with selecting actions that are not novel and are quite typical based on the prop it was given. Over time, however, it will be tasked with choosing pretend objects and actions that are increasingly more novel and unexpected. To implement this in practice, we needed 4 main ideas. First, we collected a set of pretend objects and actions to use with these props by bringing people into our lab and asking them to show us what they could do with our props. We then trained a deep generative model called a conditional variational autoencoder on this data to generate action variations, taking into consideration the physical attributes of the prop while doing so. We also used computational models of novelty, unexpectedness, and quality from the research literature to evaluate both the humans and the agent's actions and arrive at some numbers for the agent to reason about while following a creative arc. We also used an extended version of the procedural response strategies like imitation, pattern application, and transformation that I mentioned previously in Lumini and adapted them for use with our deep generative model action generator. Finally, using these strategies, the agent could generate as many action variations as time permitted, then evaluate them, and finally choose the one closest to the target creative arc. To see this in action, we created a virtual reality installation called the Robot Improv Circus, where people could play the props game with a virtual agent. This game takes place in a huge virtual circus tent with carnival music and a sold-out audience. Everyone is a robot to level the playing field of user expectations. Here's what the Robot Improv Circus looks like in action.
We have created an interactive installation using virtual reality for people to play the props game as robots with a virtual improviser agent. After familiarizing themselves with the game in a trial round, during their turn, the human is given a prop and has 30 seconds to perform as many pretend actions using that prop as possible. After completing each action, they hit a buzzer, incrementing their score before passing the prop to the agent when their time is up. When the agent receives the prop, it improvises actions using the same prop for 30 seconds, incrementing its score after each action is completed. In order to better interpret the agent's actions, the intended action and object are announced using a speech bubble and audio. When the agent completes its turn, the round ends, and a new prop is given to the human for their next round. The game ends after a fixed number of rounds are complete.
Two things to point out here. Firstly, this video was made before we changed our game format. Being asked to do as many actions as you can in 30 seconds encouraged people to ignore their partner and just think of actions for their next round while their partner was performing. Not exactly very co-creative. And secondly, even though the agent and human don't communicate directly or explicitly outside of the agent's speech bubble and voice, the agent is using its evaluation of the human's actions while negotiating its creative arc. The takeaway from this work is that improvisational action selection can be done using creative arc negotiation. You can find much more detail about the Robot Improv Circus, the creative arc negotiation technique, as well as the system design and many other details in papers and other videos at the link above. Okay, so let's recap. Within a game, we can co-create and even in some limited way improvise with AI to create emergent gameplay. But what if we want to co-create games themselves with AI, not just what happens once we build them? There's been a lot of great research in this space from a procedural content generation perspective. But as with the other parts of my talk, I'm going to focus specifically on game agents and co-creating their behaviors with AI. In the last year and a half, I've gotten the opportunity to do just that with Microsoft Research, and the rest of my talk is work done with my colleagues at MSR. Being at MSR, there was a huge opportunity to focus on co-creating game agents with real developers. So how do we help them co-create agents with AI? Part of it could be to use reinforcement, imitation, or various other machine learning methods to get the agents to learn how to play the games themselves. But given how new these techniques are for commercial use, we also don't really know what it would take for game creators to use these AI techniques in a real-world game development context outside of research. What challenges do these game creators face with their current game AI tools? And what opportunities could there be for AI to support them in their current practices or in entirely new workflows that might use techniques like reinforcement learning? To get some answers, we studied a small sample of game agent designers and developers who used either traditional game AI techniques or RL from across the game industry. We conducted semi-structured interviews with them, asking about the challenges they faced in their work processes and with their current technologies. We then used thematic analysis to understand the responses. In our AID 2020 conference paper, which was awarded the Best Paper Award, we described some of the challenges and opportunities that we surfaced for creating game agents in commercial games from three key themes around their design, implementation, and evaluation. You can see some of them on screen here. I'll briefly describe a select few opportunities that we highlighted in our paper. First, there is an inherent tension between authorial control and agent autonomy. Since RL agents have stronger autonomy than, say, behavior trees, allowing designers to exert more expressive control over RL agents is a fantastic opportunity to support agent co-creation with RL. Another opportunity for supporting agent co-creation with RL is in adapting agents across different levels or level types, or even different games. Generalization is a known challenge for reinforcement learning, but perhaps commercial games are the perfect challenge problem for targeting research breakthroughs in this area. Finally, across the board, automating game testing at massive scale was highlighted as a key opportunity for RL agents. This would free up the designer or developer to focus on other aspects of their creative process. There are many, many more of these challenges and opportunities, and we present them in our paper. You can find them at the link above. The big takeaway from this study is that game agent co-creation with reinforcement learning and other learning-based approaches faces many challenges, but also offers many opportunities for research and product impact. You can find all the details about our study in the paper and talk video at the link above. Let's talk about one of those problems in particular: designer control versus agent autonomy. As a result of our previous study, we decided to understand designer control and agent autonomy further. Rather than having designers learn to use RL the way it currently works, how could we design RL workflows to meet designers where they were and adapt to their requirements, making it more useful to them? Perhaps making it more designer-centered. Last year, I was fortunate enough to mentor our fantastic intern, Batu Aitemes, who worked with us on this problem as part of his research internship at Microsoft Research, Cambridge. This work shows some first steps towards a designer-centered approach to RL by enabling designers to customize and tweak the aesthetic style of their agents with a more intuitive workflow than the traditional process. Let's take this example on screen. The designer starts with an agent that successfully completes the task of racing to its goal as quickly as possible. But trying to get there quickly incentivizes the agent to navigate by dragging along the walls. Let's say that looks terrible for this particular game. So a designer wants to tweak its style to follow a more appropriate path, like this one. How do we make this change possible for the designer? We can start by using preference learning so that the designer doesn't need to know much about RL. Preference learning, like this version we implemented from Cristiano and others, learns to model the user's preferences between different behaviors and provides the agent an extra reward component in addition to the original task reward to get to the goal as quickly as possible. In this case, we call that additional reward its style reward. Great, so we have a style reward that helps it learn the designer's style, but when trading off between task and style rewards, a badly configured weighting between them can lead to either extreme behavior or even reward hacking. Like these two examples. So we robustly recombine the task and style rewards at many different weightings using potential-based reward shaping. Unfortunately, I don't have the time to explain the details now, but you can read much more about it in the blog post linked above. At this point, we have an agent that much more robustly combines task and style rewards given some weighting between them. But a designer still needs to provide some weights for the two reward components. And they don't have any meaningful context for how they should set them, or even what these weights mean. So we use an automatic reward scaling scheduler to replace the two weights with a minimum acceptable task reward threshold. The designer provides this threshold, and the scheduler then increases the style reward automatically, as long as the minimum task reward is preserved. So then, the thing you can take away from this work with Batu is that designer-centered RL workflows enable designers to assert expressive or stylistic control over autonomous characters. You can find much more detail about designer-centered RL in our blog post at the link above. These are the 4 key insights I'd like you to take away from my talk today. So for improvisation, learn as much as you can from users as quickly as possible, and use a technique like creative arc negotiation to solve the improvisational action selection problem. And when co-creating game agents itself with RL, know that the process faces many challenges, but there are also many research opportunities and opportunities for product impact. And finally, designer-centered RL workflows enable expressive control over autonomous characters when using RL. We can also summarize these 4 key takeaways even further as the following challenge and opportunity for the industry. First, we need more human-centered research into these AI techniques before they can be widely adopted in the game industry. Secondly, once we get human AI co-creation tools out of the lab and into the hands of creators, we will have a huge opportunity to see what magic they create. Thank you for your attention. You can reach me at these links.